Hi everyone, we'll get started now. So, welcome to a session on overview of timing constraints. And so this session is what we call Q&A session. I'll talk about a few topics in timing constraints, and then basically the session will be driven by the questions you ask. So whatever questions you are asking, I'll try to answer those questions. So we have done earlier this similar session on CDC, physical design, STA. So this is our session on timing constraints. So we'll be focusing on timing constraints. If there are questions related to other than timing constraints, I probably won't be able to cover in this session. But as in we recently created a Telegram community for asking questions. You can join that community. The link for that community is available on our LinkedIn website. So please join and feel free to ask any questions there, any mentoring questions you have, any guidance on your career you need, or any general VLSI, ED, any question you want, as in we'll be very happy to answer. So let's get started with this session. Let me cover a few very basic topic in timing constraints, and then we'll open it up for a Q&A session. So if you have any questions, type it in the chat window, and once I take a pause, I will answer those questions. Okay. Okay. So I hope you guys are able to hear me well. So the role of timing constraints, why timing constraints are important in design flow, is basically it's one of the most important item for your place and route optimization and static timing analysis. Can someone just type in the chat window to confirm you guys are able to hear me? I'll wait for someone to type in the chat window to confirm that you guys are able to hear me. Okay, great. So basically, how do you verify the timing parameters of a design? This is done using basically timing constraints. Timing constraints are important to verify these timing parameters in static timing analysis. So what kind of parameters which exists in the timing constraint? For example, what is the speed of the clock on which I'll be running my design? What will be the maximum transition which can occur on the signals, what can be the minimum transitions which can occur in the signals? When a clock goes through the design, how much delay it is allowed to encounter? When clock goes through logic of the design, it can change its shape. So what is the minimum pulse which can happen on these designs? All this information are kind of constraints or basically limitations on the design. And this information is provided using something called timing constraint. The most common format for timing constraint is SDC file, which is Synopsys Design Constraint. So this is a format which was developed by Synopsys, but it's open source now, as in the major part of SDC can be used by any tool, and this is typically what is used to define timing constraints. So timing constraints is kind of a specification for STA tool, and STA tool works or even place and route tool uses those specification and does it analysis, whether it's STA analysis or optimization using those. So that is the role of the timing constraints in a design flow. Okay. So there are multiple kind of timing constraints which exist in the design. So I'll talk about basically what I will talk about these constraints at a higher level. So you can grasp what are those constraints, why those are used, and basically then there are specific commands to specify it. I'll talk about those commands as well. So first constraint is, how do you specify to STA tool, backend tool, PNR, that this is the frequency on which I want to run my design. Okay. And this is known as constraint for timing, and this is specified using what we call clock commands. Okay. So what are the frequencies on which I'm going to run my design? It is either specified using a command known as create underscore clock command and another command known as create underscore generated clock. Create clock is a primary clock. It can be coming from outside your chip, or it can be generated on a or created on a PLL inside your design. And generated clock is a modified version of that. It can be, let's say, clock division, which is happening on that clock, or multiplication, maybe divide by 3, divide by 5. But basically, it's a derived version of your primary clock. Then there are other commands which are used, which are also indicative of what frequencies you are going to run. Set clock groups command, which is one of the important command I'll cover. It's basically how clocks are related, between which clocks you need to meet timing, between which clocks you don't need to meet timing, what is the transition on the clock, how long it for the clock it takes to rise or fall. So all these is what I'm grouping together as saying constraints for timing, and basically it impacts the timing frequency on which your design is going to run. So there is a question, I'll take a pause because I think it's important to cover that question at this point of time. So there is a question whether constraints are important for backend only or also important for front end. So it's very interesting question. As in, constraints mostly are used by backend tools. By backend tools, I mean your static timing analysis tool or your place and route tool. But constraints are also used by some of the front end tool. For example, I would say clock domain crossing or CDC tool is a front end tool. There, it's important to know what clocks are synchronous and what clocks are asynchronous. What are your clocks? So some of the front end tools also use clocks. So it's important both for front end and back end. But if you have to choose, as in more important for back end tools than front end tools. Then there are constraints for area and power. So as you can see, right, these constraints are defining how you want to design your chips. For example, first set of constraints we looked at explain what can be the maximum frequency of the design. Here you're telling what can be the maximum area of the design, what can be the maximum dynamic power which the design can consume. So this is specifying restrictions about area and power of the design. And these constraints are examples of these constraints are set max area, set max dynamic power. So these are again SDC command, timing constraints command, and you're giving that as an input to tool, either your STA tool or place and route tool to analyze design with these constraints or with these limitations, with these specifications. Then there are design rule constraints. These constraints are driven from your target technology and tells you, okay, what you can do in the design, what you cannot do in the design. Some of these examples are what can be the maximum capacitance on your design, what can be the minimum capacitance on your design, what can be the maximum transition on a signal. Transition is nothing but basically how much time it takes to either rise, a signal to rise or signal to fall. What can be the maximum value of that? What can be the maximum fan out on a net? Basically, let's say you have a net in the design, what can be the maximum number of fan out in the design? The larger the number of fan outs, the as in the delays will change, the signal may not, the net may not have enough strength to drive those fan outs. So these limitations which are coming from technology, your target technology, you are implementing your design on 45 nanometer, 22 nanometer, 5 nanometer, 3 nanometer, though that is your technology. And these requirements are being driven from your technology and being used here and being provided as a constraints for your design. Then there are constraints for interfaces on the design. What I mean by interfaces, when you have a design, let's say this is your design. There are some signals which are going outside the design. There are some signals which are coming from outside of the design. So these are your output ports. These are your input ports. Okay. And there needs to be some constraints to be specified on designs, which are kind of assumptions that, okay, maybe this signal is being driven by this kind of buffer, this signal is being driven by AND gate. Though in order to meet timing in this portion of the design, you have to specify what are the assumptions tool has to assume on the boundary of this design. Some of these assumptions are like what kind of cell is driving an input port. This is given by set underscore driving cell command. What is the delay on the input? For example, let's say you have this design, okay, and you need to meet timing on this port, and this port is coming from outside the design. So delay means what part of the logic, or what delay, basically what portion of, what is the delay which is taken by this logic which is outside the design, that is specified using input delay command. Once you know that delay, let's say this is D, and then what is delay here, and you know setup and hold, you can try to meet timing within this portion of the design. Similarly, set output delay, you are asking, providing an information how much delay is outside the design on the output side. So this is this. Let's say you have a flop here going to output port. So what is delay consumed? What is the delay value of outside the design that you specify on this port here? So this is so basically, in order to meet timing, you need to know what are the outside information, what is the driving cell which is defining it, what is the delay on the input and output. These are specified using these constraints for interfaces. What is set load specifies what is a load on the output port, what kind of capacitance it is driving, and that is specified using set load. So there are constraints or commands for specifying the boundary condition or interfaces. Then the constraint to put the design in a specific mode or configuration, and it's basically assumptions on some certain signals where only certain values are allowed. For example, set case analysis, it tells use to specify a certain constant value on a signal. For example, let's say you have two clock, test clock and functional clock, and a select line is driving it. Let's say you want to do your analysis only in functional mode, okay? Then in order to do that, a certain constant value will be specified here. And let's say select one, you will mark select to be 1, and only functional clock will propagate. This you can specify using the set case analysis command. Set case analysis does not change the design, but basically it puts this signal to a value 1 without actually connecting it to power or VDD in the RTL. So tool takes this as an assumption and does it analysis by assuming this signal to be whatever constant value you are specifying. Similarly, you can specify set logic don't care on certain signals, set logic 1 or set logic 0. Set logic 1 and set logic 0 and don't care are more used by synthesis tools, so that basically based upon this they can further optimize the RTL and while converting to gate. Set case analysis command is more used in your STA and PNR tool to time or optimize in a particular design mode. Then there are timing exceptions. Timing exceptions means, as you might, so these are exceptions. Okay, typically or normally, every path in design, flop to flop, flop to latch, you need to meet timing in 1 cycle, setup timing in 1 cycle, and hold timing in 0 cycle. Okay, timing exceptions commands allow you to change that default timing behavior. So these are exceptions to normal behavior. Normal behavior is that you have to time all your paths in 1 clock cycle. These timing exceptions change the normal behavior and create exceptions for those. For example, set false path command. So normally you will time the path in 1 clock cycle. Set false path says you don't need to time these paths. So you have a flop to flop path and you add a timing exception on that path. If you add using set false path, that means normally you need to meet this time path in 1 clock cycles timing for setup. But if you have added a set false path, then you don't need to meet timing. Typical conditions when you have false path, maybe logic is not useful, maybe it's a dead logic, those kind of situation. Set multi-cycle path says normally you meet the timing. I'm talking about set of timing. Normally you meet the timing in one cycle. You can change this. Okay, you can change this using set multi-cycle path. You can say, okay, I need to meet this timing in 2 cycles, 3 cycles, or maybe you can reduce. You need to meet it in half cycle. So you can specify those using set multi-cycle path. Typically, this set multi-cycle path is used when there are multiple frequencies of clock involved. For example, let's say you have a fast clock and you have a slow clock. And if you're changing data only on this edges, you're not changing data on this edge, then you don't need to meet timing in one cycle because your capture is coming here and here. And if you're not changing here, this is not possible. So only need to meet timing in 2 cycles. So that multi-cycle path changes the default behavior from one cycle to different number of cycles. And typically this is used when multiple frequencies exist in the design and you're ensuring that one cycle path timing is not needed. Then there are set max delay and set min delay. So set multi-cycle path changes in terms of cycles. Set max and set min delay changes in form of the delays on the design. Set disable timing is used to disable certain arcs in the design. But at a high level, set exception commands change the normal or default behavior of analysis. Either it set false path says don't meet timing, set multi-cycle path says don't meet timing in one cycle. So it changes the normal behavior to a modified behavior using these exception commands. Okay, so I have covered basic commands. What are the basic commands in your design? I'll take a pause here. If for these commands you have any questions, if for any general constraints related questions you have, then I will cover a couple of more topics for during this session. So there is a question, this SDC file is used for STA only, or is it used for other purposes also? So SDC, it's actually SDC. It's used for multiple purposes. One of the purpose it is used is definitely for STA, static timing analysis. Other purpose it is used to give input to your PNR tool as well. It goes as an input to your synthesis tool as well. And it is also used by your CDC tools to do clock domain crossing analysis. So this is a general purpose file which is used in multiple flows. But primarily it was developed for STA, but now it has expanded to other tools as well. So again, taking a pause here and waiting. If there are any more questions, please type in your questions and I will try to answer. Then I will cover a couple of more topics related to timing constraints. So please type in your questions. I'm taking a pause of a couple of minutes to see if there are more questions on this commands I have covered or any other thing related to timing constraints. So this is Q&A session. So please type in your questions, whatever you have related to timing constraints. Okay, so there is a question on what is time budgeting. Okay, so let me try to answer that. Let me find some. Okay, yeah. So what is budgeting? Okay, so let's say you have a big design. Okay, let's say you have this SOC design, and it's not possible to, let's say it has multiple blocks. This block and this block, and let's say this is block 1. And this is block 2. Let's say this is very big design. Okay. So it's not possible to time this design using, let's say, completely flat by a single tool. So then what you have to do is you have to time or optimize each block separately. So let's say one block you will optimize separately. Block 2 you will optimize separately. Okay, and that is what you want to do. Now, in order to do that, just a minute, I think someone, please keep yourself on mute if someone is not on mute. So in order to time this, let's say you have one path here, flop here, coming from here to here. Okay. Now, in order to do that, this, let's say, is both are running on the same clock as 10 nanosecond. Now, in order to time these paths when you're doing at individual level, some delay you have to give here. Okay, so some delay will be in this path. Let's say this is 3 nanosecond. I will say this is, let's say, 2 nanosecond, and this is 5 nanosecond. Okay, now this full path has 10 nanosecond delay. The maximum allowed delay on this full path is 10 nanosecond. You need to divide these delays into what block 1 delay will be, one block 2 delay will be, and specify those while timing or optimizing block 1 and block 2. So you'll say, okay, for this path, I will give block 2, block 1, 3 nanosecond delay. Rest I will give 2 nanosecond, I'll give it in the top, and 5 nanosecond I will give here. So you're kind of budgeting or defining what delay would be part of each path. And this is known as time budgeting. Time budgeting is nothing but basically giving what part of the clock period or delay a block will consume. And then you can now time this block separately or optimize this block separately, optimize this block separately. And this is what is known as budgeting or time budgeting. And this is typically when your blocks are big and used in hierarchical flows. So I hope this covers your question. There are more questions. Let me go. What are pulse width violation and why they are important? Okay, so this is a very good question. Let me, okay, yeah, I hope I have space here. Yeah, okay. So what happens, okay, let's say you have a clock in the design, okay. Let's say this is a clock net. Now, clock goes through multiple logic in the design, okay. This is, let's say, logic 1, logic 2, logic 3, okay. Now, typically what happens is, ideally on clock path, when clock is rising, okay, the delay through this logic should be same as when clock is falling, okay. So when clock is rising, the delay through that logic should be same as when clock is falling. Ideally, that should be the case. That's the ideal situation. Now, practically, it is not always equal. Designers try to make it as equal as possible, but it's basically practically they may or may not be equal. Now, what happens because of that is, let's say you have a clock here, okay, and let's say rise and fall delays are not the same. So basically, when the clock rises, delay is like this, but when it falls, the delay is less. Okay, or if so now it goes through first logic, it changes like this. Now let's say same thing happens in second case. Rises, delay is more, falls, delay is less. Now what can happen because of this, as you see here, okay, the width of the pulse, if there is a difference in the delay, width of the pulse can start reducing. If one delay is more than the other, depending upon whether rise delay is more or fall delay is more, the pulse either on the rise pulse or the fall pulse can start changing its shape and it start reducing its width. Okay. Now, if the width becomes too small, it may not be desirable and can may not be seen by the flop. Okay. If the width becomes too small, it may not be seen by the flop. So now, what minimum pulse is allowed in the design? It is either mentioned in your design technology library or you can give it as a constraint as well. An STA tool makes sure when the clock propagates in the design, your pulse width is not lower than minimum width. And this is known as pulse width check. So to summarize, pulse width checks check that your clock pulse is not lower than the minimum value which is allowed in the design or in the technology. And SDA tools check that. What is the reason for pulse width or what is the reason for clock pulse reducing is it's because of the delay in the clock network. Rise delay and fall delay in a clock network can be different, although designers ideally try to make it same, but if there can be practical limitations and these can be different and these can lead to pulse reduction. If pulse reduction is lower than what is the minimum pulse width that should be, the STA tools will report pulse width violations and these are known as pulse width violation. Okay. Okay, there are more questions. That's good. Keep them coming. So there is something called set timing derate command. You're right. As in there is a question on there is something called set timing derate command that is used for OCV. I have confusion like OCV, derate, and PVT variables both are same. So you're right. They are used in similar context. Set timing derate, your OCV, on-chip variation, and your process voltage and timing variations. They are similar in nature. What has happened is in previous, like these processes have evolved. Okay, so earlier, maybe set timing derate command came earlier. It just derates the path. What it does is, let's say you have a path with 10 nanosecond delay, you can say derate factor of 0.1. It will derate, or in for maximum path, it will increase the delay by 1%, 0.1, and I mean, for minimum delay timing, it will decrease that path. So these basically were developed in different stages. Like PVT corner process, PVT corner is process voltage corners, which is basically typically in a design. Let's say voltage can vary from 1 volt to 0.9 volt, and your libraries are characterized as per that. So this came maybe slightly later than set timing derate. Uh, and when later on people started realizing, okay, maybe three corners are not enough, they started going into more corners. Then OCV came in, which is for on-chip variation, which is more continuous or more continuous modeling of your variation across chip. So all those are used for similar purposes. In advanced technology, you might use a more thorough like OCV kind of analysis because that is more relevant. But all these are used for similar purposes. Is basically when you create a die or a chip, right? So on a die, there are multiple chips. There can be variations between different chips on a die or variation within a die. So AND gate here and AND gate here may not be exactly same. So delays can be different, or AND gate within this chip here or here may not be exactly same. And that is what you're trying to capture using PVT corner, set timing derate, or on-chip variation, or commonly known as OCV. Okay, but purpose is same, but the techniques they use are different, and some are more advanced than the previous generations. But at a high level, the purpose of this is same. So there is a question on budgeting. So regarding budgeting, do we also have to account for crosstalk, or it's just pure delay? Budgeting is what I would say is budgeting is not like it's not an absolute like science. It's there is some arts involved in that as well. Okay, so now depending upon what clocks are interacting, you may need to account for crosstalk as well. The more accurate you are, the better you would be in trying to when you go to the timing at the top level. The less accurate you are, uh, the if you're less accurate, then you'll have to do more work at the top level trying to meet these timing across blocks. So the more accurate you are, help, but more accuracy comes at the cost of doing more work at lower level. So there is a trade-off involved. Usually, so it varies from company to company. Some may not account for crosstalk, but then you just have to do a little bit more work at a higher level. These days, like for example, Primetime or STA tools actually do automatic budgeting for you as well. So that there you can uh, consider more. Basically, as this is done by tool automatically, it can be more accurate, and you can push down or write down the lower level constraint. Are pulse width violations only check for clock paths? Okay, that's a good question. I have only seen it in the context of clock pulse, but I think it can be typically for any signals. For any signal, the pulse width yeah, so it can be for any kind of signals, but typically it's more worrisome for clocks. Uh, and I would say typically for normal signals, if you're meeting setup and hold paths, typically the pulse width violation should not occur, but typically it can be for any signal. Okay, so there is another question. What are the ways to reduce pulse width violation? I would say the ways to reduce pulse width violation typically on the clock paths is to use or design cells, which is typically done, is to have same rise and fall delays. And in a library, you would really see that when you're using, there are cells buffer to be used on clock paths are created separately. So they'll, let's say if you want to add a buffer on the clock path, you might use a different buffer than what you would use on a data path. And the reason for this is exactly this, that you want to ensure the rise and fall delays on the clock paths are same. So typically separate buffers, gates, cells are designed to be used on clock paths, and that is the way to reduce your pulse width violations. Okay, so I'll go to the next topic, which one of the important commands in constraints analysis, which is set clock group command, and then I'll come back to more questions. Meanwhile, please keep typing in your questions as you see fit, and I will cover those in the sessions. Okay. So one of the important aspects when you have multiple clocks in the design is synchronous and asynchronous clock. Okay, so what are synchronous clocks are basically clocks where event happens in a fixed phase relationship, which means that the edge of the clocks are there is a known timing behavior of edge of the clocks from in terms of their rise or fall edges. There is a known relationship or a fixed phase relationship. You know when this, if this clock is rising here, you know it is going to rise at the same time or a defined delay or period of time. So synchronous clocks are clocks which have a fixed phase relationship between each other. Now, what the advantage of synchronous clocks are typically derived from the same PLL, or same. They are typically either same, coming from the same PLL. One is divided of another. So basically, they are derived from each other typically. And you can it STA tool can only time, or PNR tool can only time between synchronous clocks only. The other set of clocks where there is no fixed phase relationship, that basically, and that can cause, basically, if there are no fixed phase relationship, then setup and hold cannot be timed on those clocks. Why it cannot be done is because you don't know what is the relationship between the edges of this clock. So if rise edge of one clock comes, you don't know when the rise of edge of other clocks is going to come, because there is no fixed phase relationship. Those clocks are known as asynchronous clocks. So between asynchronous clocks, you cannot time using STA, or basically timing tools cannot time between those clocks. There you will not be able to meet setup and hold time, and that's why they are checked using what you call CDC tool or clock domain crossing tool. Then there are logically exclusive clocks. These are clocks basically which are logically exclusive. Logically, on only one of the clock can be present in the design. For example, let's say this is the clock. There is C1 clock and C2 clock, and there is select line, a mux here. Now, when select is 0, C1 is going to propagate. When select is 1, C2 is going to propagate, but only one of those clocks can propagate here. So the logic, because the logic condition of the design, so these clocks are then known as logically exclusive clock. So because of the logic condition in the design, only one clock can propagate, either C1 when select is 0 or C2 when select is 1. These clocks are known as logically exclusive clocks. Physically exclusive clocks are clocks which cannot coexist in the design. If one clock is there, the other clock cannot exist in the design, then these clocks are known as physically exclusive clocks. So let's say you have a clock, okay, and this is coming from outside the design. Okay, let's say there is a mux here. So C1 and C2 are coming. On this net, when it comes to this block, only one of the clock can exist. You cannot have two clocks on the same net, because mux will either select one clock or mux will select other clock. So you only have one clock, then these clocks are known as physically exclusive. Physically, only one of the clock can exist. Okay? Then those are known as physically exclusive. So synchronous clocks, asynchronous clocks, logically exclusive clocks, physically exclusive clocks, all these relationships are defined using a command known as set underscore clock underscore groups command. Okay. Here you define what clocks are synchronous, asynchronous, logically exclusive, and physically exclusive. STA tool by default assumes all clocks are synchronous to each other, and then based using the set clock groups command, you can change the default behavior from synchronous to something else. Okay. So this is one of the example where using set clock group command, you are specifying clocks to be asynchronous of each other. Okay. So how it is specified is, you specify the command set underscore clock underscore group, use an option asynchronous. That means you're telling something about asynchronous behavior of the design. Then you use called group option. Using group option, you are saying that this pair, this group, and this group are async to each other. Note that you are saying relationship between those two groups. So that means clock 1, this group has clock 1, is asynchronous to clock 4, clock 5, and clock 6. This means clock 2 is asynchronous to clock 4, clock 5, and clock 6. Clock 3 is asynchronous to clock 4, clock 5, clock 6. So you are telling one group is asynchronous to another group. There is no relationship which is being told between this group itself. So you're not saying clock 1. This does not mean clock 1, clock 2, and clock 3 are synchronous. You are only telling relationship from one group to another group. Okay, but there is no relationship which is being told using this command between members of its own group. You are only saying clock 1 is asynchronous to clock 4, clock 2 is asynchronous to clock 5, clock 3 is asynchronous to clock 6. There is no relationship which is being implied by the command between the same group. Okay, so this is one of the important aspects to understand about set group command. Similarly, you can specify clocks. Basically, you can specify logically exclusive, physically exclusive, all these things using the set clock group command. So when you're saying asynchronous, use asynchronous option. The other options are logically exclusive, physically exclusive, those options. By default, all clocks are synchronous in STA, but using set clock group command, you can change that synchronous to asynchronous, physically exclusive, and logically exclusive. Okay, let me take another pause and see what more questions which have been asked here. Okay, so there was a question, why can't we use normal buffers in clock path and avoid pulse width variation? Normal buffers, you typically don't have same rise and fall delays, and that's why special clock buffers are designed to use that. I think someone already answered that question. I'm just repeating it. Okay, good question. What is the difference between logically exclusive clocks and physically exclusive clocks? Are they same? Are they changeable? Yeah, good question. So, logically exclusive and physically exclusive, let's come to that. Okay. So, logically exclusive clocks are when both of the clocks can exist in the design, but logically only one clock will propagate. So, both exist, but only one will propagate. And only one will propagate because of the logical condition of the design. Physically exclusive is when both cannot exist in the design. Okay. Now let us understand this more clearly using an example. Okay, so let's say you have a mux in the design. This is C1, C2, and select. So both C1 and C2 are present in the design. Okay, but because of the select condition, only one will propagate here. Either C1 will come here or C2 will come here. Okay. Physically exclusive is when both cannot exist in the design. So same thing, I will say mux here, but that is outside the design. So you are defining two clocks here, C1 and C2, because which is coming from outside design. On this net, only one can exist. So then basically it is physically exclusive. Now let's say in this case, logically mux case, before this mux, both can exist, but after this mux, only one can exist. So let's say you create new clocks in this output of this mux. Let's say generated clock 1 and generated clock 2, okay, which is divided by one version of C1 and C2. Then GC1 and GC2 are physically exclusive because only one can exist in the design. So logically exclusive and physically exclusive are typically because the same reason, either clock muxing or clock gating. There is, however, a minute difference. One, physically exclusive, only one clock can be present in the design. Logically exclusive, both clocks can be present, but logic condition of the design will cause it to only one to propagate. Now, why it is important to be precise here is let me explain. Okay, when two clocks can be present or not present together, it impacts how timing tool times those clocks. When two clocks can be present together, C1 and C2, then there can be crosstalk between these two clocks. Okay, so these two clocks are present together. That means when this is rising, if this is not rising, there can be crosstalk, and this can cause some signal bump to come here because of the lumped capacitance. So if two clocks can be present in the design together, STA tool will calculate crosstalk between them, and one clock can change slightly the delay or rise or fall of other clock, and the STA tool will take that into account while doing timing. But if two clocks are physically exclusive, there is no crosstalk which is possible between those two clocks. So it's important to specify those information to STA tool so that the STA tool can do accurate analysis. Now coming back to our mux case, between these two clocks, C1 and C2, these are, I'm saying logically exclusive because they can be present in the design together. So STA tool actually needs to check crosstalk between these two clocks or calculate crosstalk. That's why I'm saying this to be logically exclusive. Now let's say I created two clocks here, GC1 and GC2. Only one of the clock will exist, and let's say they go to different paths, then there is no need to calculate crosstalk between. So whether the two clocks can be present together in the design on the same net or not, basically, can they be present together in the design? If they can be present together in the design, but logically only one clock of will propagate, you will typically specify them as logically exclusive. If they cannot be present together at all in the design, then you will say them to be physically exclusive. And it impacts how STA tool does crosstalk analysis or calculation between those two clocks. Okay, so I covered what is the difference between logically exclusive clock and physically exclusive clocks. Again, I'll take a pause here, wait for more questions, and see if there are more questions on timing constraints. Please, if you have any questions, type it on your chat window and I'll take those questions. Okay, let me see if there are more questions which are asked. Does not look like there are more questions. Please type in your questions in your chat window. Uh, I'll wait for a couple of more minutes to see if there are more questions. Okay. Does not look like there are more questions today. So this was our session Q&A session or timing constraints. We do have full course available on timing constraints, both in video format and in the written format. You can check it on our website. And as I was mentioning earlier, we have created a Telegram group where people can interact with me, ask their questions, take career guidance in VLSI and EDA field. So the link for that is shared on our LinkedIn page. So do check it out and join the Telegram group. And if you have any personal questions using that Telegram group, you can also personal message me to ask specific questions. Thank you everyone for joining this particular session. If you are really interested in timing constraints, we do have a full video course available. The recording of this free session will be shared on our webpage and on our YouTube and on our LinkedIn page. So follow our LinkedIn page so that you can keep getting regular updates and subscribe to our YouTube channel. And thanks a lot, everyone, for joining today's session. Thanks a lot. Thank you.
Sir,
Sorry, yeah. Is there a question?
yes, sir. Sir, can you tell me what is setup, negative setup time and negative hold time, and how can I
Sure.
convert it into positive setup time?
So today's session was on timing constraints. Please join the Telegram group, and I will answer that this particular question related to STA specifically on that channel. Is okay.
Okay, sir. Thank you.
So the Telegram group link is mentioned on our LinkedIn page. Do follow that.
Okay.
Thank you, everyone, for joining this particular session on timing.